Welcome. In this video, we look at Chapter 3C, Other Bases. Now, we saw earlier in 3B, the early numeration system's place value, that the Babylonians had a base 60 system, and the Mayans had a base 20 system. Of course, we use a base 10 system, but that makes us think maybe there are other bases that we could use, and so that's what we'll talk about today. Like, for example, what would a base 6 number system look like? We'll talk about binary and hexadecimal numbers, that's base 2 and base 16. Those are used a lot in computer science. And then we'll just think about other bases in general. All right, let's get into it. So just as an example, let's consider base 6. What if I wanted to do arithmetic in base 6? What would that look like? What do base 6 numbers look like? A good place to begin is thinking about what digits are needed. Now, for us, with base 10, what are the digits that we have? It's 0 through 9. So in base 6, the digits will be 0, 1, 2, 3, 4, and 5, and then I'll stop. I don't actually have a digit that represents 6. Kind of like in our system, we don't have a digit that represents 10. We go up to 9, and then we start repeating back at 0. So looking at this table to the right, there are the normal numbers, base 10, 1 through 14. Let's see what happens if I just start counting up in base 6. So I have 1, 2, 3, 4, 5, but then I can't write 6. Nope, get rid of that guy, because I'm not allowed to. I don't have that symbol in a base 6 arithmetic. Once I get to 5, I have to wrap back around to 0. Well, what happens is 5 wraps around to 0, but the digit to the left gets increased by 1. In this case, there is no digit to the left, so I put a 1 right there. And so in base 6, 1, 0 really means the same thing as 6. Right? 1, 0 in base 6 means 6. Now, how do I actually read that number out loud? Do not read it as 10. It is not 10. If I wanted to, I could read this in two ways. I could read this as 1, 0, base 6, or I could just simply read this as 6. That really is, honestly, that is the number 6 in base 6 arithmetic. Okay, let's keep on going. What comes after 1, 0? How about 1, 1? Then 1, 2, 1, 3, 1, 4, 1, 5. And now the 5, I've gotten to the end of my digits, it wraps around to 0, and the digit to the left increases by 1. So now I'm up to 2, 0. In base 6, 2, 0 is the same thing as our number 12. And then it continues 2, 1, 2, 2, and so on. Let's try writing a few consecutive numbers in base 6, starting with 5, 2, 4, 4. So instead of starting with 1, I'll just pick some random number higher up and we'll go from there. Now look at this. I put a little subscript SIX. That's a nice way of denoting a number that's in a different base. If I just write a number without a subscript, 5, 7, that's understood to be 57 base 10 in our normal system. If you really want to be explicit about it, you can even write TEN as a subscript, just to be sure that we're talking about 57 base 10. Well, at any rate, back to the problem at hand. Let's begin. 5, 2, 4, 4, and I'll not write the SIX because in this context it's understood. What comes next? 5, 2, 4, 5. Oh, okay, and then, let's see, my rightmost digit is increasing, but, so it wraps around to 0, which means the one to the left increases by 1. So 5, 2, 5, 0. Let's keep going. 5, 2, 5, 1, 5, 2, 5, 2, 5, 2, 5, 3, 5, 2, 5, 4, 5, 2, 5, 5. Oh, this is where it's getting interesting now. I need to increase that rightmost 5 by 1. It's going to turn it into a 0, which then increases the guy to the left of it by 1. Oh, so that turns into a 0 as well, and the one to its left increases by 1, giving us 5, 3, 0, 0. This is a little bit like in our system, if I got to the number 7,299, after that becomes 7,300. In base 6, what number comes before 4000? All right, and again, that's not the number 4,000. Don't read it as 4,000. So let's give it a try. What number comes before that? Well, we're tempted to write 3999, right? It seems like our intuition would tell us in base 10 that works, but we don't have nines in a base 6 system. What's the biggest number we have? What's the biggest digit we have? It's just 5. Oh, so in fact, what I really get is 3, 5, 5, 5, base 6. And if I just want to kind of test it out, maybe I could check by adding 1. If I added 1 to this, what would happen? The 5 increases to 0, which increases the guy to the left, which makes that a 0, which bumps up the guy to the left, makes that a 0, which bumps up the 3, and makes it a 4. Right, so there we go. So this, the number preceding 4000 is really 3555. Well, let's continue and write a few consecutive numbers backwards from 4000. Before that, 3555. Before that, 3554. Before that is 3553. And before that, 3552. Let's keep on going down at least until it flips over. 3551. 3550. Okay, now here's the interesting part. What's going to come next? I'm going backwards, so I want to decrease the 0, which makes it flip around to a 5. And so I'm going to subtract 1 from the number that came before. And by subtracting 1 from that 5, it gives me 4. So I end up with 3, 5, 4, 5. All right, let's continue on. Is this guy, 3610 base 6, is that a valid number base 6? It is not, and what you see here is because of that digit 6. Nope, that never appears in a base 6 number. The only digits I have are 0 through 5. Well, how about this guy? I check it out, 42205. Yep, those all look like valid digits, so that is a number in base 6. But then that makes us think, what is the actual value of that number? Like if I convert it to our system, what is it? Just to give me a sense of its actual size. So let's do this. Here's how we do it. In base 6, our place values are powers of 6. Just like we saw in our system, base 10, the place values are powers of 10. In the Babylonian system, base 60, the place values are powers of 60. And in the Mayans, base 20, the place values are powers of 20. So here we go. Let's multiply all of our digits by the powers of 6. Starting on the right, I multiply by 6 to the 0, and then moving left, times 6 to the 1, 6 to the 2, 6 to the 3, 6 to the 4. And when we do that arithmetic, and then add all those together, we get 5,693. Now I can legitimately say that number, that is our base 10 number. So how do you pronounce this guy if you say it out loud? You say it, 5,693. I know it's kind of weird. If we grew up with base 6, then this number would make total sense to us and we'd have a sense of its size. But we didn't grow up with base 6, we grew up with base 10. So the bottom number is the one that's more meaningful to us. We kind of have a general sense of how big 5,693 is. Binary numbers. So let's turn our attention to base 2. We have so few digits to work with, 0 and 1, that's it, that it can almost be a little bit tricky. So let's start writing the first few numbers. So, well, 1, and then how do I write 2? I want to increase that digit by 1. I'm tempted to write 2, but I can't. I'm stuck already. So I wrap around to the beginning, 0, and I stick a 1 out front. Okay, let's add 1 to that rightmost digit. 0 becomes 1. Good. Now let's add 1 to that rightmost digit. The 1 flips back to 0, and I have to add 1 to the guy before. Oh, but adding 1 to 1 is going to make that flip around to 0, and I get a 1 out front. Continuing on, the rightmost 0, that becomes 1. So 1. Then adding 1, the rightmost 1 flips back to 0, and the one next to it gets increased. Okay. And then I can add another 1 to the right. That 0 becomes a 1. The other guys stay. And we'll do one more. The 1 on the far right, when I increase it, it flips around to 0, but then I have to add 1 to the next one over, which flips that to a 0. I have to add 1 to the one there. That flips around. and I eventually add a 1 on the far left. What are these actual numbers? Well, these really are the numbers 1, 2, 3, 4, 5, 6, 7, and 8. In base 2, I write the number 8 as 1, 0, 0, 0. In base 2, I write the number 6 as 1, 1, 0. How about you? You try this. Write the base 2 numbers from 1 through 20. So I already got you started with 1 through 8. Pick them up from there and finish out through 20. All right, give it a try, and then pause the video and then unpause the video when you are ready to check your work. All right, welcome back. Let's see how you did. Here they are. Here are the base 2 numbers 1 through 20. So see how you did. It's really interesting to look at these things and kind of see the pattern of how it goes. And it feels kind of good if you can start to see the pattern and the rhythm and start just keep on writing down one number after the other in base 2. That's kind of cool. In binary, let's write the next few numbers after 1, 0, 0, 1, 1. So right after 1, 0, 0, 1, 1, the rightmost digit increases by 1, which makes it flip around. That becomes a 0. And which increases the digit next to it, which then also becomes a 0, which then increases the one next to that, which then becomes a 1, and everything else stays the same. 0, 1. Now I will increase the rightmost digit. That just becomes a 1. So 1, 0, 1, 0, 1. Now what happens when I increase the rightmost digit? It'll flip into a 0 and change the 0 next to it into a 1. So 1, 0, 1, 1, 0. There we go. Now when I increase this by 1, I'll take that rightmost 0 and just make it a 1. So 1, 0, 1, 1, 1. Now what? That rightmost 1 increases, but then it flips around to make a 0, which increases the value next to it, which flips around to a 0, which increases the value to its left, which becomes a 0, which finally hits the 0 there and turns that into a 1. So we end up with 1, 1, 0, 0, 0. How will I convert this binary number into a sort of a normal base 10 number? Well, we do that again by using powers of 2 as the place values. So I'll write down my digits, so 1, 1, 0, 1, 1, and now write down powers of 2. This is times 2 to the 0, times 2 to the first, times 2 squared, 1, times 2 cubed, 1 times 2 to the fourth. And so we get, let's say 2 to the fourth is 16. 1 times 2 cubed is 8, so that becomes 8. 0 times anything is 0. 1 times 2, which is 2, and then 1 times 1. Remember, 2 to the 0 is 1, so I get a 1 there. And when I add all these together, I get 27. So there is our base 2 representation of the number 27. Now, here's a different way you might think about converting 11011 into base 10. And it's a slightly different way, and it just works for binary numbers. I write out the digits, 1, 1, 0, 1, 1. And then underneath, starting from the right, I'll write down 1, and I'll just keep doubling it as I move to the left. So 1 doubled becomes 2, doubled becomes 4, doubled becomes 8, doubled becomes 16. So I've really just written the place values down below, these powers of 2. And then anytime there's a 1 up above, 1 among my digits, I'll just circle the numbers I created down below. And those are exactly the powers that I keep. So I can just add those circled numbers. And when I add those, 16 plus 8 plus 2 plus 1, I get 27. Base 16 numbers. These have a special name. These are called hexadecimal numbers. Now, if I'm in base 16, I need digits that go up through 15. So I need a different symbol for values 0 through 15. What we do is we start with 0 through 9, and then we augment our digits by using the first 6 letters of the alphabet. Really, this A has a value of 10. B has a value of 11, C is like a 12, D is 13, E is 14, and the F is 15. So a number in hexadecimal might look something like 4A92E. And if that's my first number that I begin with, how do the next few numbers go after that? Let's see, 4a, 92e, 4a, 92f, and now what? Let's see here. After f, I increase the f, but the f doesn't have any place to go, so it wraps around to 0. So that becomes 0. And I look to the left of that, and I have to increase that digit by 1. So the 2 gets boosted up to a 3. So 4a, 9, 3, 0. And then 4a, 9, 3, 1, 4a, 9, 3, 2, 4a, 9, 3, 3, and so on. You know what? Actually, let's keep on going. Let me ask you, what happens? Eventually, I'll get 4a, 9, 3, 8, 4a, 9, 3, 9, and then what? Do you see what number is going to come next? 4a, 9, 3, 9, I need to boost up my rightmost digit, and what comes after 9? It doesn't wrap around to 0. In the hexadecimal system, 9 is followed by a. So the next number is 4a, 9, 3, a. And then 4a, 9, 3, b. And then 4a, 9, 3, c. And so on. I'll not keep on going after that. Let's take that same number, the one that we started off with, 4a, 9, 2e. And what is that in base 10? Let's put that into our normal number system. So what do you think we do? We take the digits from before, 4a, 9, 2e, and I'll multiply these by powers of 16. Right? This is a base 16 system. But something to take care of, what is this a times 16 cubed? What is e times 16 to the 0? Well, a really represents 10, and e really represents 14. So when I do my arithmetic, I can replace the a with 10, and I can replace the e with a 14. And now, when I multiply these all together, add them up, I get 305,454. So this number that's over 300,000 was actually expressed in hexadecimal with 5 digits. And so the hexadecimal is actually a little bit more concise than our system. You can see that this number in our system is written with 6 place values, but in hexadecimal it only takes 5 places. You know, other bases are possible, and you can use any base you want, as long as it's a natural number greater than 1. For example, you could work in base 12, and we might consider the digits 0, 1, 2, 3, all the way up through 9, and then add x and e as our extra digits, where x represents 10 and e represents 11. So if you did arithmetic there, that's called the duodecimal number system. Or perhaps you could go really big. Take base 64. Well, you need 64 different digits to be represented, including 0, and then the highest digit represents 63. So maybe you could use, say, 0 through 9, and then capital A through Z, and then lowercase a through Z, and then stick on a couple random symbols also. How about a plus and a slash? In fact, base 64 isn't just something I made up, but believe it or not, it really is used in computer science. In fact, a lot of data on the web is transferred in base 64. They convert numbers into this system, and then it gets transferred as text. You could work base 3. In that situation, your only digits are 0, 1, and 2. This has a name. This is called the ternary number system. So any base is possible. How about base 5? Let's take a random base, 5, and a random number, 4231, base 5, and let's express that in our system in base 10. What do? Actually, pause the video, give this thing a try, see if you really understand the process at this point, and then when you are ready to check your work, start it up again. All right, give it a try. Okay, we are back. Let's see how you did. We take 4, 2, 3, 1, and multiply them by powers of 5, starting at the right, 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, and the answer we get is 566. Alright, we have seen a lot of base arithmetic in this lesson. This stuff is kind of interesting. I like it because it opens our ideas to new possibilities of what number systems can be. And it sheds light on our own system, the base 10, and we see how base 10 is really just one situation of something much more general. Alright, I'll stop the video here.